Greetings and welcome back to Paleozoic PCs. I know it's been a long time. Don't have an excuse. Just bad at YouTube. So, today I'm going to try something a little different. I'm going to try to show hands-on tinkering today. So, when we last left, at the end of my last video, I talked about creating new prototypes of those memory boards for the Tandy 1000 EX and HX series. And then of course I disappeared, didn't talk about them. So here they are. If you remember from my first video, the concept of I was using these 100 by 100 millimeter size boards because they're very cheap, and building various expansion components for a machine that had otherwise been bare. So in the original set of boards, I had a memory board, I had an IDE board, and I had a serial board. Well, with that last build, I combined the memory board, I combined the serial and IDE boards on one board. I kept the memory board separate, but I did add more options. Like the original board was really designed just for an EX, so it kind of wasted upper memory space. It gave you the full 128K of upper memory in an EX, but you could only use 64 of it in HX. So this version of the board I designed to allow up to 96K of memory for an EX, for an HX, and it also allows you to selectively move around certain things like the location of the ROM. So in principle, if you had something else that required an option ROM, like a VGA card, you could use this with that. That required the addition of one more decoding IC. So the original board used 3 ICs for the decoder. I had to add another decoder for this one. So the other thing was basically exactly the other two boards combined. I added one more chip to this one compared to the chip count of the other two in order to put the serial behind the same buffer as the IDE port, and that worked, although I did actually discover one program that would not run properly on this board that ran on the old one. And I think it may be a timing issue because the chip select has to get cascaded through this chip that does the AND operation. So the buffer opens slightly later than the serial port is open. So I wonder if that's it. I haven't been able to was not able to pin it down exactly. Everything else worked. It was just Kermit that would have problems with transfers with this board. So with everything basically working, I pretty much hung this up for the last few months. But now I'm back because I didn't feel like it was really worth just trying to combine these together. Because A, they worked as it was, you know, it's a perfectly valid solution for expanding an empty one of these because there's room for 3 cards. This is only 2. I didn't have any other cards I wanted to reuse. It's compact, it works. And also, there simply wouldn't be anything to be learned by packing this down. So the last few months, I've been trying to jump start into the world of programmable logic, and starting out with Fisher-Price, my first programmable logic, which is GALs, generic array logic. Generic array logic is the primitive ancestor of today's CPLDs and FPGAs. It's basically kind of like a EPROM chip in that it has a memory, which is a series of fuses that sets selectors inside that it has essentially a chain of OR and AND gates available to each output, and it chains together which input pin they listen to and how, based on the state of those input pins, it changes the state of the output pin. So I've started learning how to program those, and it seemed like, you know, to come up with, as my next project, to just go ahead and finish this whole Tandy memory board project by eliminating as much of this discrete logic as I could and combining it into area logic for this final board. And of course, I wouldn't want to just do the same thing over again. So this new board, in addition to all the memory functionality of this board and all the serial functionality and IDE functionality of this board, you may notice this has two big black memory chips on it. It has a flash chip and a RAM chip. This has the flash chip, and it has three of these big SRAM chips. So this board actually also implements 1 megabyte of LIM EMS compatible RAM. It's driver compatible with, there's the company Low-Tech makes a series of expansion boards, which I recommend if you need one for your normally slotted PC. This is driver compatible with their 2 meg EMS board. It is implemented differently, but it is driver compatible. And hypothetically, it would support up to 4 megs of memory, but this is the biggest chip you can find in through-hole. So, one new challenge at a time. So, what are we doing outside today, besides it being a beautiful day? Today, I'm going to show you how to fix it if you screw up with your PCB board design. So, first off, I will preface by saying one advantage of the programmable memory logic is if you get the traces on the board right, but you get your logic wrong, it's very simple to simply flash a new program into the programmable logic. I mean, I've tested pretty much everything on this board at this point, and I will say that I had some problems, but every problem up to this last one, and technically one more problem, but I'll talk about that later. But every problem I've run into until I hit this wall, I was able to fix by simply reprogramming that chip. This has 2 programmable area logic chips on it. Now if we compare this to the old board, one of the reasons I liked doing 2 boards for the old system, and was actually kind of not that inclined to combine them, was there are 20 address lines in a PC compatible like the Tandy 1000, and for memory you mostly are concerned with decoding the top half of those 20. And for I/O, because it uses this port I/O system in which there are 1024 possible ports, you're only concerned with decoding the bottom 10 of the I/Os. So, as you see, you generally need, I mean, if you want to just decode one I/O port, you can use something like a 688, which is just one chip. But if you want to do anything more complicated than that, you're generally talking 3, 4, 5 chips to decode the 10 address bits that you want for I/O, and you're generally talking at least 2 or 3 address bits to, on this machine you're probably talking about 3 or 4 address bits you want to decode for memory, and that's still going to be 3 or 4 chips. So in the end, I did succeed in that we have 1, 2, 3, 4 decode chips on this. We have 1, 2, 3, 4, 5 decode chips on this. Every one of those functions performed by those 5 chips is now being performed by these 2 chips. And in addition to that, they also do the EMS decoding for this with the help of these 2 chips I've added right here, which are '74 LS670 register files, which are essentially small dual-ported RAM chips. And what they're used for is EMS requires a small memory, which is used to implement the pages, the page registers for the doing the dynamic remapping of the memory space. You know, EMS has a 64K window that it places 16K pages in. These page registers store the state of all of those 4 pages. It provides the offset that says for this 16K window, start at this location in this memory chip. So that's 9 chips replaced with 2, and in the process getting enough extra logic to, with the help of a couple register files and more memory, being able to implement EMS RAM. And in fact, I actually have a couple extra inputs and outputs left over on those chips. So it's quite an improvement. It actually has a lower chip count than these boards. So what did I do wrong? So I tested everything about this board. I had to fix some I/O decoding equations to get the IDE port happy. The serial port, I made a boneheaded mistake with my decoding logic, which is I forgot. So this chip on this basically implements 2 of 16550 serial ports. It's called a 16552, and it has 2 independent 16550 serial ports on it. But the way they're implemented, when I programmed the chip, I programmed it as if I had 2 separate serial chips, so it provided a single chip enable for each serial port on here. And I forgot that the way this chip actually worked is it does have 2 independent, it has 2 lines, but they're not independent. It has a chip enable and it has a serial select. So if the chip enable is a 0 and the chip select is a 1, it picks serial port A, and if chip select is 0 and port select is 0, it picks serial port B. But again, because of this logic is programmable, it was a simple fix to just fix it. So everything is all working in that area. You may notice this has a dip switch on it. This is, I've eliminated most of the jumpers. I do still have some jumpers to select IRQs for the serial ports, but all the previous options that I used to set with jumpers, like the address of the serial port on this one, and on this one, the paging areas of the memory, that has all been replaced by dip switches. And the way those dip switches work is they actually feed into inputs on the GAL. And the position of these switches, there's a pull-up resistor pack right here. And depending on whether this is grounded or allowed to float, that actually changes the equation that takes effect for the various options. So you can select alternate serial port locations, you can select the memory address of the ROM chip, the EMS page, the memory map. There's a mode page as to whether this is plugged into an EX or an HX. And there's actually also a base backfill disable. So I don't have one to test it in, but this card, if fitted with a ISA card adapter, should be able to work in other models of Tandy 1000 or even a generic PC to supply everything, all the upper memory block, clock calendar, IDE functions. Just disable it trying to fill the bottom 640K with that 384K So again, what did I screw up? So it was a stupid brain fart because I had it right when I first sketched it out, but it got lost on translation into the schematic, which is the register file. It essentially acts as a dual-ported memory, and it has input data lines and has output data lines, and it has a read signal and a write signal, and essentially you can at any time write a value into it at the same time a value is being read out the other side. So the way that this chip, the pair of the chips together supply 8 bits. Each of these only has 4 bits on it. So the write data lines are decoded on the I/O bus. They're decoded at 260 hex, and a value written into them when stored in the memory here is output constantly out the other side. And the other side is connected to the upper address bit. Well, it's connected to both some of the upper address bits on the memory chips. So like the bottom 14 address lines are connected up so they supply the 16K directly to the CPU. But then I believe it's the next 6 address lines are connected to it's 5 address lines. Next 5 address lines are connected to the bottom 5 bits of this 8-bit register we've created. And by changing that, it changes the location within the chip of where the page is being taken from. And then the upper 3 address bits are fed back into the memory decoder gal. So this is the I/O and this is the memory. Just like how this is split into 2, the functions here are split into 2. We have the address, we have memory functions, and we have I/O functions. So the last 3 bits are actually fed back into the memory decoder, and it supplies the chip select signals to decode these 2 chips. Now if I had a larger, denser chips, which I'd have to go surface mount for, I could use those 2 chips to select, say, 2 1 megabyte RAMs instead of 2 512s. Or I could even, if I had 2 megabyte chips, which is I think the largest you can get in 5 volt, you could actually select 2 of them and have up to 4 megs. That's great, but the one thing that I just completely brain farted on is everything else I/O on this board and everything memory on this board has both a chip select and then they have memory read and write strobes. And the memory read and write strobes are supplied directly by the ISA bus. So the thing that I brain farted on was that the 670 here only has a single line, which is a write strobe, and that write strobe has to happen only when this chip's being written. So essentially the decoder has to implement, has to get the chip select for the address and has to combine that with the write signal to actually get the strobe. So I forgot about that, and I did not run the write signal from the ISA bus to the I/O decoder to be able to do that equation. So when I was trying to troubleshoot this, I was seeing that like it would sometimes see a page of RAM if I ran check it or something to say there was RAM here, but I went to basic and was writing stuff to the RAM and discovered sometimes there'd be RAM there and sometimes there wouldn't be. So instead of busting out the fancy oscilloscope, I pulled out the old logic probe. If you remember Tron, bring in the logic probe. Took the old logic probe, connect it to I think it's pin 12 on one of these registers, and of course that should only be strobing when you're writing to the register. If I output something to 260, and instead I sound it just randomly strobing away. Bing, 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 bing. So anyway, one look at the schematics, big forehead slap, realized that any time hex 260 was appearing on the bottom 10 bits of the address bus, it was flipping on the right signal, because it didn't decode it and say, okay, well, it's hex 260, but it wasn't looking for the I/O write signal. So it was just flipping that on, and basically whatever happened to be in flight on the bus when Hex 260 appeared was getting written to the registers, so they were essentially randomly flipping memory around. So that's what we're going to fix today. As you see, I was able to verify this was the problem because I had an unused input on one of these gals, the correct gal, because it's the one that's decoding the address, but and so I could just run a jumper. You see I've pulled the pin out of the socket and ran it to the pin on the I/O bus and rewrote the formula so it listens for the I/O signal there, and it works. I will demonstrate the board later, but can't exactly have this as a permanent addition if I want to test things. So today what we're going to do is this pin 14 on the gal, unfortunately, because supposedly good practice, I tied the unused inputs to ground. So what we're going to try to do is we're going to try to free up that pin from ground, run a wire on the back side, solder it in place, and then hopefully we'll be good to go. So let's talk a little more about our game plan here. I will zoom in the camera for a better look. So here's an unpopulated copy of the board. Now if we look at pin 14, don't know how well you're going to be able to see this, but this board, first let's talk about how these PCB boards are made. If you look at the PCB board, you see there's light colored parts and there's dark colored parts. The light colored parts are where there is still copper underneath the solder mask. Dark colored parts are where the solder has been eaten away. So you notice on the back, there's more of the lighter color than on the front. The reason is, it's generally considered good practice, I guess. I don't know. I'm not a scientist. To have something of a ground plane. Now, of course, on a two-layer board, two-sided board, you can't exactly have like a full ground plane. But essentially the workaround is just leave whatever, you etch out the traces, and of course you etch out the gutters around the traces, and then the idea is when you design the board, just fill the rest of it with copper. Now on the older boards, I actually just filled the back, and on the front I had to etch off all the other copper. So I've read that you can go ahead and fill both sides, and so filled both sides, and both sides of the fill is connected to ground. Now there's seem to be religious wars about this. There's some people that say what you should do is you should fill the other, you should put the fill on the other side, connect it to like VCC, and then that gives you a tiny bit of capacitance across the entire board. And that kind of works like the decoupling capacitors. And the counter argument is that these boards are so thick that the amount of capacitance between it would be negligible. So I elected to go with ground on both sides. And part of the reason I did that is you can see that the traces are very dense on this. This board was not fun to route. I don't use an auto router. I had to weed this all by myself. Part of the reason why I thought ground on both sides would be a good idea is because it was actually getting difficult with the density of traces to be able to carry ground everywhere where it was needed. So, in some places there are vias that poke and connect the ground on one side to the other. So there are ground pins that are connected via these fills on one side, and that fill goes somewhere and then pokes through the other side next to the ground. Now, my understanding is if this was an analog board, this actually might be bad practice because it causes something called a ground loop, where you get like an uneven length between signals. Seems to work fine. Fingers crossed for digital. But anyway, so pin 14 here, if you look, it is connected to a tiny little chunk of ground plane on this side. It's not connected to any other pins on this side. It's just a little chunk. There's a via that punches through this other side. And then, I've already scratched this one up, but you can see the via comes here and then is connected to the ground pin on the chip. So that's pin 12. It's connected via this little thing and this via. So the best way I figured out to try to free this pin up is actually this via is right next to pin 13, where it dives through, is I just took a little screwdriver and I just kind of gouged out around that via to scraped off the copper. So that's what we're going to do on this board. We're going to go ahead and that's the guy right there that we want to gouge out. So I say with much trepidation, we're going to go ahead and try to do that. Just using a little flat bladed screwdriver worked fine. These boards are surprisingly tough and well built for something that cost under $2 a shot. So let's see. I think I gouged that out pretty good. Let's check it. So what we want to see on my old Radio Shack DMM here. I think it's Radio Shack. I don't know. It's made in Korea. I have a much nicer, newer one that does beeps and stuff, but I do not know where it went. So what we want to make sure is that we have no continuity between pin 12 and pin 14. And it looks like we have achieved. No. It looks like we still got some current going through there. Yep. Gouge it some more. All right. Let's try it again. It looks like we've killed it. Excellent. And this also demonstrates the ground connects every ground on this. So like if we connected this ground to say this ground, you can see all the grounds are connected. So we're not, if this was connected somewhere else, then it would also flow through. So I think we have done the needful in terms of gouging that out. Let me just make certain for sure, because we do not want this gouging out our grounding out our IO right line. Yeah, it looks good to go. Okay, so the pin that we want to solder to is we look on my schematic over here. Here's the bus. IO right. It's pin B13. Let's just double check that's what we did. Not blow away. 1, 2, 10, 11, 12, 13. So we will count. 1, 2, 3. We're going to count it with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'll put this as 12. So the pin here, this should be the one that we want to hit. So I can actually test that that is the right pin by just going ahead. Got my multimeter here. We're still clipped to the other side. Go ahead and hook that on there. And let's poke what our pin is here. Here. It's connected here. And poke it. And we have a winner. So, plan is to use a little of this wire wrap wire. It's nice and thin. Let's see, how long do we need? Not particularly long. We only need to go from here to there. So we should just strip off a little of this. Tell you what, we'll go ahead and try to connect that. Now we'll cut it to length. All right, soldering iron's about hot. This is the part I love because I'm not very good at soldering. Let's put a little bit of solder on this thing. I think we should pretty much just be able to heat up what's already there and just kind of glip this in there. But you're going to see me at my worst right here. There we go. Okay. Doesn't look too bad. I guess we could verify we still have the right wire. So let's double check. Did we get the right wire? We got the right wire. So guess now we get to do the fun part, nailing that back down again. So we want to get it to pin 14 right there. Got a little bit too long a tail on there, I think. Do not want it shorting any adjacent pins. Come on. Come on, baby. There we go. All right, let's do the same thing again. Let's get a little dab of goodness on here. And maybe use these to help. Oh, that sits way too high. I don't like that at all. There we go. That I think I can live with. Okay. So now, at this point, I can remove the clip. Now, one thing you may have noticed from the points of my boards is I've tried to replicate the same expansion bus configuration as the original Tandy card, which was the pair of 62 pin connectors of different heights so they can go through. Well, it's impossible to find a single high connector. So my previous boards, I would always just stick two of them and then I could use a stacking header like you might use for a Raspberry Pi or something on the outer one to lift it up. Now, one thing I did notice eventually, I would have noticed this quicker if I had the original boards, but of course the whole reason I started this is because I didn't. The original board, these headers are taller than on my board. So these are standard height headers. These stand about a little under a ½ inch tall when they're snug down on the board. And I realized that when I stack these guys together, so I've only got with this stack, the boards are about ½ inch. The original Tandy stacking is 0.7 inches, so it's almost a ¼ inch taller. So I decided to fix that with the new board, at least for the inner connector, which is the one where a board stacks originally on top, which is I found you can get these double-ended headers, basically for connecting two female headers together, and they have the same length pins. So I came up with a jig for holding that straight while I just soldered the ends of the pin in to the board. So you see this sits above it, and that actually puts that at about the right height. I've tested it with one of the only original Tandy board I have, which is a modem, and it sits at about the right height. So I left the outer one disconnected for now because I have several different things I want to try there. So we'll talk about that later. But in theory, you could stack again like this, and then if you used a high enough stacking header, you could again get to the correct height to mate with the original board. Again, another idea I had for this board was I mentioned that I can disable the backfill of the original memory. If you wanted to stick this in a 1000 EX or HX that has the original board, you can actually, I think you could actually just put the female header on the bottom. You could put it in the outer position, just put it here instead of in the middle. And this board is actually narrow enough that it would fit in either height, but it would fit in the inner one without a problem. It's only about 100 millimeters wide. It's not wider. So you could actually use this if you wanted to add 2 serial ports and EMS memory and a clock and IDE and stuff to the original board. I mean, the only reason I would see for keeping the original board is for some reason you want to have the DMA chip. Again, the only really practical result of not having it is certain floppy disk software won't like you don't have a DMA chip. But anyway, we're all soldered up. We should be good to go. Let's try it in the machine. And there we go. The computer's still booting. That was the EMS driver testing RAM. It identified 64 pages, which is what it has with 1 megabyte of memory available. So the operation was a success. So let's go ahead and pop in to check it and just count all the fingers and toes, make sure they're still there. I could type. All right, configuration. As you see, we have 624K of RAM. That is what you expect from a Tandy 1000. We have a 2 gigabyte drive C in the form of that flash adapter I was plugging into the board before I plugged it in. And we have a 1024K at segment A000. Now, if you're familiar with PC architecture, you might say, wait a minute, why is that memory there? That's where VGA and EGA live. Well, this machine doesn't have EGA or VGA, so that 64K is open. I talked about this at least in a forum. I don't know if I mentioned it in an earlier video. There's some part of the service manual for the original 1000 makes it sort of unclear about whether the A segment is ever used when it's shuffling around the 128K that's built into the original Tandy 1000, whether the internal memory ever resides there. I've done much experimentation and it does not appear to be a problem. So the default setting of this board is to go ahead and map the page frame at this address because it gives it to us for free and lets us have the maximum amount of upper memory blocks. It is an option to move it to a higher location at the cost of upper memory blocks if you were trying to make this card get along with a VGA or EGA card. But anyway, so we have 2 COM ports. Starting a mouse is fine. Now, one thing you may notice, we have 1024K, only 512K is available. That is because I have a 512K RAM disk set up. So, look at the memory map. This always takes forever to render on an HX. Okay. We have the EMS page at E000. We have video memory. We have the second page, 16K of video memory, which is part of the Tandy double maps. It always fills 32K, even if it's just a double map. So that's, in this mode, would be a shadow of the first 16K of memory. But you see, that's normal for it. It misidentifies it as high memory. But at C00, we have 8K of ROM. It identifies that as a video ROM because that's where EGA and VGA ROMs usually reside. That is actually the XT IDE driver. There is another 8K that is unoccupied. And then we have this. The memory mapping of this board actually makes 112K of ROM available, of upper memory available. So you see we have 64K of DOS and drivers in this area. And we have 48K of memory available. And then there's the ROM that's standard in an HX. If this is plugged into an EX, this would be either open or would be RAM depending on where we position the ROM. So one thing that I have done with this is if we look at the interrupts, you will see devices with no IRQs COM2. That is not actually true. So COM2 usually resides at IRQ3. Now, I have made it an option with this card to assign IRQ2 to a serial port. And I have it assigned to IRQ2, which is why it identifies it as belonging to the mouse. The reason I did this is one of the network cards that I've been using, its driver does not like to use IRQ2. So I've been using an alternate driver for that. And I wanted to see if the actual driver for it worked any better. So I specifically designed this so it will get along with that particular network card. If you didn't have that problem, you would probably want to assign IRQ3 to COM2. But this board has the option to move it, and the Qt mouse driver has no problem. So if you consider COM2 as a mouse port, this configuration is perfectly valid. So. Dismembering. We'll just do the quick test. And there we go. Successful test. This benchmark's the same as the board did before, so. As before, these scores are slightly higher than a similar machine that has the original Tandy board because there's no overhead from the DMA sucking up a little bit of bandwidth. I mean, it's only a few percent, but is what it is. Hard disk. And again, about 500K a second as it was before. It's actually inconsistent. Sometimes it scores up as fast as 560, sometimes it scores this, but it's the same as before. So, in any case, this is as fast as a one-to-one interleave MFM drive in a PCAT, so I'm not going to complain about that. So, there we go. So I alluded earlier that there's one other problem on this board in terms of layout, and I can go ahead and show you that. So this board uses a flash chip, uses an SST brand flash chip, 39F010, I think. Don't quote me on that. Anyway. So previous revisions of this board, the first one assigned a whole 64K to the flash chip. The next one, I had to actually add one chip so I could cut the resolution down a little bit and still have it movable around. I mean, if I just wanted it fixed at one location, there is a more efficient decoding system, but in any case. Next version used 32K, so it could take it to the top of the bottom half of the C page. So this revision, I thought, arbitrarily, hand-wavingly, well, if it doesn't mind, it's a 128K flash chip, it must not mind being divvied up. So I designed this board to only expose 16K. And it can expose that 16K either at the beginning of the C page, or it can expose it in the top half, the top quarter of the C page. And that is for, on the rare case that you might want to mix this with a VGA card or something else that requires C00, you can do it. So I only ran the first 14 address lines to the flash chip. So now, if I go to this flash directory, I can show you. There's no harm in trying because it can't do anything. I can try flashing. The BIOS I'm currently using. Now you see it saying unable to determine flash chip type. Well, that was a bit of a surprise to me because it had correctly identified the SST chip in the previous version of the board. So you see it's attempting JEDEC programming. So the way this works is these flash chips have a write signal run to them, but they don't act like a RAM chip. Basically, in order to write to these flash chips, there's essentially a sequence where a secret handshake has to occur. You have to have a series of reads and writes against certain addresses in the chip to basically unlock it, and then you spoon feed it the new bytes. You can also send it commands to like do like a sector erase. So like these flash chips are divided into, say 128K one will be divided into a number of like 16 or 32K sectors. So the issue at stake here, and this is why you should always read the data sheet when you're designing a board, is I neglected to discover that the secret handshake for this SSD, so you see it erased, it timed out, it expects FF, that means these chips have all bits ones when they're erased, but it found 55H. That's what's supposed to be there when it's programmed. So let's go ahead and reboot anyway, just in case. Just to demonstrate we didn't hurt anything. It turns out that the secret handshake for this particular chip, the addresses involved are at like 4K into the chip, I think. I don't have the book in front of me. Maybe I should. But the second secret handshake location is offset hex 5555 from the start of the chip. Well, if you do the hexadecimal math, that's a little bit under the 24K mark. So, yeah, by not running the A14 address line to the chip, I can no longer program it in place. So it wasn't a huge deal. I have a programmer and pull the chip out and write a different value to it. But turns out you can't just cut it down to 16K. I've got a solution to that. If I make any more of these boards, I think what I will do is I will go ahead and run that extra address line, and then I will set up the dip switch location. So if the board is in full memory for an HX mode, which is have the ROM chip all the way down at the bottom so it can fill the rest of the C page up with RAM, then I will have it expose only 16K of it. But if you set it to have all the RAM outside the C page, like you would in an EX, if you're not using anything else in high memory, then I will have it put it at C800 and expose 32K of it. So worst case, if you have an HX, all you would need to do is reach in there, flip the dip switch to EX mode, to the EX ROM high mode, and then program it and then flip it back, and then it would be fine. It would put it back down and only expose 16K of it. You just have to have it in the high position to program it. I will probably go ahead and test that by soldering a jumper wire on these on this board later. But it's the EMS thing I wanted to fix because I wanted to free up the bus connector for further experiments with my network card and such. So that is probably enough blathering for today. Hopefully I will not go away for another 5 months. If anyone's watching. Nobody's watching, then whatever. Have fun out there in YouTube land, everybody. Thank you.